At the end of this session, you will be able to enter the program to perform the use of timer as an event counter to count external events and check the result through port 2 and record the observation. Introduction to timers and counters. 8051 has two timers or counters: timer or counter 0, timer or counter 1. Timer is used as a time delay generator. Clock source is the internal crystal frequency of 8051. 8051 timers use 1/12 of crystal frequency as the input of timers. Before writing the program, we will see the number of ports and the pins of the ports. The 8051 microcontroller has 4 parallel I/O ports labeled as P0, P1, P2, and P3. Each port is 8-bit wide and has a total of 32 input or output pins. P0 port 0, pins 32 to 39. P1 port 1, pins 1 to 8. P2 or port 2, pins 21 to 28. P3 or port 3, pins 10 to 17. Counter is used to count the number of events on registers. It has an external input from TX input pin X is equal to 0 or 1. We use TX to denote T0 or T1. External input from T0 input pin P3.4 for counter 0. External input from T1 input pin P3.5 for counter 1. Next, we will look at the tools and equipment needed to use of timer as an event counter to count external events. For this, you will need the following tools and equipment such as PC or laptop 1 number, microcontroller kit 1 number, USB cable 1 number, FRC cable 2 numbers, Flash Magic software, and Keel Microvision software. Let's now see the procedure for using a timer as an event counter to count external events. It involves 3 steps. Step 1. Write the program for 8051 microcontroller using Keel software. Step 2. Burn the converted file using Flash Magic software to the microcontroller IC. Step 3. Assemble the circuit by connecting the hardware parts and execute the output. Now we will run the program using the software called Keel Microvision software. Switch on the computer and open the Keel Microvision software. Once you have opened the software, click on Project and select New Microvision Project. Create the file name as per the project. Here, it is named as Timer as a Counter. Click Save to proceed. A tab pop-up appears to select the microcontroller. Here, we are using the 8051 microcontroller. So select AT89C51 from the database and click OK to continue. Click on No to add the startup.A51 to the project folder. On the left side of the screen, a tab called Project appears. Click on the plus sign beside Target 1. Now Source Group opens. Right-click on the Source Group 1 and select Add New Item to Group Source Group 1. Select the .asm file since we are writing the program in assembly language. Name the file. Here, it is named as Timer as a Counter. Click on the Add to add it on to the Source Group 1. Now start entering the program in the .asm file created. org00h. Set origin to address 00h for starting the program memory. Move t mod, /60h. Set timer 1 mode to mode 1, 16-bit auto reload. Move th1, /00h. Initialize timer 1 high byte to 00h. Move TL1, /00h. Initialize timer 1 low byte to 00h. Set B P3.5 semicolon. Set bit of port 3 5th pin, 15th pin of the IC as the input port and pin as the input clock pulse. L1 colon set BTR1. Create label L1 and set the bit of timer 1. L2 colon move A, TL1. After setting the timer 1, create another label L2. Move the value of timer 1 low byte to accumulator. Move P2, A. Move accumulator A value to port P2. When there is an external pulse by the input port, the value will be displayed by port 2 in the form of LEDs. JNB TF1, L2. Jump to label L2 if timer 1 overflow flag TF1 is not set. CLR TR1. After performing all the actions, clear timer 1, run control bit, stop timer 1. CLR TF1. CLR means clearing timer 1, overflow flag TF1. SJMP L1. SJMP means short jump to label L1, loop back to start of the program. End. Type end to end the program. Now navigate to the target and right-click and select Options for the target 1. Change frequency to 11.052 MHz. Select the box of the Use on Chip ROM. Now go to Menu and select the output. Enter the hex file name in the name of executable. Here, it is timer as a counter. Select the box of Create Hex File and click OK to continue. Navigate to the menu and select Translate and check whether there are any errors or warnings. In the build output, it will show the number of errors and warnings. Now next to Translate, there is an icon named and click on the build target. In the build output, it will be displayed Creating Hex File from Timer as a Counter. Timer as a counter, 0 errors, 0 warnings. Turn on the microcontroller kit after entering the program in the software. Now connect the laptop to the microcontroller kit using USB cable. Connect one end of the cable to the laptop and other end to the microcontroller kit. Now click Windows on the keyboard and type FlashMagic to burn the code. Now in step 1, select microcontroller. The microcontroller specification will vary from kit to kit. Here, we are using 89V51RD2. Now for selecting the COM port, click on Windows and type Device Manager. Navigate to ports COM and LPT and check the port number. Here, it is COM19. Now open FlashMagic, select COM port as COM19. It varies from kit to kit. Select baud rate as 9600 and interface as None, ISP. Click on the box of Erase All Flash to erase all the programs previously done in the kit. Now go to Step 3 Firmware and browse the hex file created and select the hex file. Navigate to Step 5 and click on Start. Now click on the Reset button in the microcontroller unit to dump the program into the kit. Now locate the external push button and see the pin number of the IC in the microcontroller kit. Here, it is connected to pin 15 of the microcontroller kit. That is, it means port 3, 5th pin, that is timer 1. Connect the ports according to the program. Locate the ports, switch and LED in the kit. Use FRC cables female to female for connecting the ports.
Here port 2 is connected to the LED. Connect the port 2 to the LED.
Now click the Reset button to start the program burning in the kit. Navigate to the external switch and give the external clock pulses by pressing the switch. As we can see, when the switch is pressed for once, the LEDs will be in 00000001 state, indicating the count of the clock pulses. Continue by giving the external clock pulses and see the change in the LED state. As the clock pulses increases, the LED will be changing. The maximum we can give is only till 11111111 FF.
This brings us to the end of this session. In this session, we have learned programming the timer as a counter for counting external events and design the timer as a counter for counting external events using the 8051 microcontroller. Thank you for watching. We will see you in the next session. Hello and welcome to this session. Today, we are going to demonstrate how to enter simple programs using 8051 microcontroller. One program will operate 8-bit addition and the other program will operate 8-bit subtraction.
Objectives. At the end of the session, you will be able to execute the program to operate 8-bit addition and execute the program to operate 8-bit subtraction. Now let's look at the tools, equipment and materials needed to perform addition and subtraction and connect it to the 8051 microcontroller. For this, you will need the following tools and equipment such as 8051 microcontroller trainer kit with instructional manual and keyboard 1 number. Now let us see how to perform addition of two 8-bit numbers. Firstly, turn on the power of the microcontroller kit. Navigate to the power button and turn on the switch. Now for writing the code in the microcontroller, externally connect a keyboard to the microcontroller at the designated port. Now we will start entering the program in the microcontroller kit. Click A in the keyboard as we are writing the code in the assembly language. Click Enter to proceed. Now give the origin for the microcontroller. Here we are giving it as 4200. The origin starting address will change from kit to kit. Start entering the program. CLRB. This clears the register B and sets it to 0. Double enter to write the next line of the code. Enter MOV DPTR, #4500. We are assigning the data pointer register with an immediate value of 4500. In this address, the output will be stored. Double enter to write the next line of the code. Enter MOVA, #17. This moves the 8-bit number 17 to the accumulator A. Double enter to write the next line of the code. Enter ADD A, #12. Adding the 8-bit number 12 with the value currently in the accumulator. Double enter to write the next line of the code. Enter JNC 420D. If carry flag is set to 0, jump to this address or otherwise go to the next address. Double enter to write the next line of the code. Enter INCB. This increments the register B by 1 when the carry flag is set. Double enter to write the next line of the code. Enter MOVX at DPTR, A. Moves the content of the A register to the external memory address. Double enter to write the next line of the code. Enter MOVA, B. Moves the content of the B register to the A register. Double enter to write the next line of the code. Enter INC DPTR. Increment the DPTR register by 1. Double enter to write the next line of the code. Enter MOVX at DPTR, A. Moves the content of the A register to the external memory address. Double enter to write the next line of the code. Enter SJMP. Type the same address displayed on the screen and press enter. Now type .enter to exit the code. Now we must verify the code before executing. For that, click U and enter. Now in the screen it will display origin. Give the starting address of the code, that is 4200, and click enter. Check each line and click enter to check the next line. Once you have verified, now click .enter to exit. For executing the program, enter Go starting address, that is 4200, and click enter. The display will show executing. Now click on the reset button. For displaying the output, enter SP and the data pointer address as we stored the value in it. Here it is 4500 and click enter. The addition of the two numbers 17 and 12 is being displayed as 29. Hit the enter key to view the carry. 00 is the carry that is shown. Let us now look into the subtraction of two 8-bit numbers. Now we will start entering the program in the microcontroller kit. Click A in the keyboard as we are writing the code in the assembly language. Click enter to proceed. Now give the origin for the microcontroller. Here, we are giving it as 4200. The origin starting address will change from kit to kit. Start entering the program. MOV R0, #00. Initialize the register R0 with 0. Double enter to write the next line of the code. Enter MOVA, #25. This moves the 8-bit number 25 to the accumulator A. Enter SUBBA, #12, subtracting the 8-bit number 12 with the value currently in the accumulator. Enter MOV DPTR, #4500. We are assigning the data pointer register with an immediate value of 4500. In this address, the output will be stored. Double enter to write the next line of the code. Enter JNC 420F. If there is no carry, borrow, jump to this address or otherwise go to the next address. Enter CPLA. Complement the accumulator, inverting all the bits in A. This operation changes each bit from 1 to 0 and from 0 to 1. Enter ADDA, #01. This adds the immediate value 01 to the accumulator A. Enter INCR0. This increment the register R0 by 1 when the carry flag is set. Enter MOVX at DPTR, A. Moves the content of the A register to the external memory address. Enter INC DPTR. Increment the DPTR register by 1. Enter MOVA, R0. Moves the content of the R0 register to the A register. Enter MOVX at DPTR, A. Moves the contents of the A register to the external memory address. Enter SJMP, type the same address displayed on the screen and press enter. Now type .enter to exit the code. Now we must verify the code before executing. For that, click U and enter. Now in the screen it will display origin. Give the starting address of the code, that is 4200, and click enter. Check each line and click enter to check the next line. Once you have verified, now click .enter to exit. For executing the program, enter Go starting address, that is 4200, and click enter. The display will show executing. Now click on the reset button. For displaying the output, enter SP and the data pointer address as we stored the value in it. Here it is 4500 and click enter. The subtraction of the two numbers 25 and 12 is being displayed as 13. Hit the enter key to view the borrow. 00 is the borrow that is shown. Now for changing the number, click on reset. Type SP4200 and click enter. According to the address, replace 25 with 12 and 12 with 25. Now type .enter to exit the program. For executing the program, enter Go starting address, that is 4200, and click enter. The display will show executing. Now click on the reset button. For displaying the output, enter SP and the data pointer address as we stored the value in it. Here it is 4500 and click enter. The subtraction of the two numbers 12 and 25 is being displayed as 13. Hit the enter key to view the borrow. 01 is the borrow that is shown.
This brings us to the end of the session. In this session, we have learned to execute the program to operate 8-bit addition and execute the program to operate 8-bit subtraction. Thank you for watching. We will see you in the next session. Hello and welcome to this session. Today, let us learn to check the reading of an input port and send the received bytes to the output port of the microcontroller using switches and LCD for the input and output.
Objectives. At the end of this session, you will be able to
Enter the program to interface LCD to display string and check the result through ports and record the observation. Introduction to Liquid Crystal Display or LCD. LCD stands for Liquid Crystal Display, a flat panel display technology commonly used in electronic devices such as televisions, computer monitors, etc. LCDs are preferred due to their low power consumption, thinness, and ability to display alphanumeric characters and graphics. A 16:2 LCD means it can display 16 characters per line, and there are 2 such lines. In this LCD, each character is displayed in a 5:7 pixel matrix. This LCD has 2 registers, namely command and data. The command register stores the command instructions given to the LCD. The data register stores the data to be displayed on the LCD. Now let's look into the pins of the 16:2 LCD display. LCD has 16 pins in total. These pins include the data lines, control lines, power supply lines, and contrast control lines. Data lines D0 to D7. These lines are used for transferring data between the microcontroller and the LCD. In a 8-bit mode, all 8 lines D0 to D7 are used. In a 4-bit mode, only the higher order data lines D4 to D7 are used. When sending commands or characters to the LCD, the microcontroller sets the appropriate data lines to the desired binary values. These data lines are then latched by the LCD when the enable E signal is toggled, transferring the data into the LCD's internal registers. The control lines in an LCD interface with an 8051 microcontroller play a crucial role in managing data transfer and control operations. There are typically 3 control lines: RS register select, RW read or write, and E enable. RS determines whether the data being transferred is a command or character data, with RS is equal to 0 indicating a command and RS is equal to 1 indicating character data. RW controls the direction of data flow, with RW is equal to 0 for write operations, microcontroller to LCD, and RW is equal to 1 for read operations, LCD to microcontroller, although read operations are less commonly used in LCD interfacing. E-enable initiates data transfer by latching the data present on the data lines into the LCD's internal registers. Typically, there are 2 power supply lines, VCC and GND. VCC supplies the required operating voltage to the LCD, usually plus 5 volt. GND serves as the reference point for electrical potential. Contrast control. Depending on the type of LCD, a contrast control pin may be present to adjust the contrast of the display. Clear display 0x01 clears the display and returns the cursor to the home position. Address 0. Return home 0x02 returns the cursor to the home position without clearing the display. Set cursor position 0x80 plus address sets the cursor to the specified address on the display. Display on or off control 0x08 turns the display on or off. Entry mode set 0x06 sets the cursor move direction and display shift. Function set 0x38 sets the interface data length 8-bit or 4-bit, number of display lines usually 2, and character font 5x8 dots or 5x10 dots. Cursor or display shift 0x10 shifts the cursor or display left or right. Next, we will look at the tools, equipment, and materials needed to check the reading of an input port and send the received bytes to the output port using switches and LCD with a 8051 microcontroller. For this, you will need the following tools, equipment such as microcontroller kit 1 number, keyboard 1 number, and FRC cables as required. First, turn on power of the microcontroller kit. Navigate to the power button and turn on the switch. Now for writing the code in the microcontroller, externally connect a keyboard to the microcontroller at the designated port. As we are writing the code in the keyboard, it is externally connected. Check whether the switch is in the external mode. Now we will start entering the program in the microcontroller kit. Click A in the keyboard as we are writing the code in the assembly language. Click Enter to proceed. Now give the origin for the microcontroller. Here we are giving it as 4200. The origin starting address will be changing from kit to kit. Now enter MOV A, P1. This means moving the port 1 value in the accumulator A. Double enter to write the next line of the code. Now enter MOV DPTR, #4500. We are assigning the data pointer register with immediate value of 4500. In this address, the output will be stored. Double enter to write the next line of the code. Now enter MOVX at DPTR, A. MOVX means moving the external instruction. At DPTR, this indicates the address in external memory pointed to by the DPTR or data pointer register. Double enter to write the next line of the code. Now enter SJMP. Short jump to the same line of the code. Enter the same address after SJMP. Double enter to write the next line of the code. Now type comma plus enter to exit the code. Now we have to verify the code before executing. For that, click U and enter. Now in the screen it will display origin. Give the starting address of the code, that is 4200, and click enter. Check each line and click enter to check next line. Once you have verified, now click comma plus enter to exit. Navigate to port 1 and switches. Connect port 1 to switch according to program using the FRC cables. Now toggle switches to the 1110 EE condition. For executing the program, enter Go starting address, that is 4200, and click enter. The display will show executing. Click on the reset button. For displaying the output, enter SP and the data pointer address as we stored the value in it. Here it is 4500, and click enter. The display will show according to the switch's condition. Here it is 1110, that is EE. Click reset button to execute another example. Now let us toggle the switches to A5. For that, start from LSB. Toggle the switches in 10100101, that is A5. For executing the program, navigate to the keyboard and enter Go and the starting address. Here it is 4200. Then click enter. Now the screen will display executing. For performing the next action, navigate to reset and click on reset. Now type in keyboard SP and the address of the data pointer, that is 4500 here. Click enter. On the screen, it will display the switch's position. Here it is A5 10100101.
This brings us to the end of this session. In this session, we have learnt programming the LCD to display the data and connecting the LCD to 8051 and displaying the data. Thank you for watching. We will see you in the next session. Hello and welcome to this session. Today, we will take you through the step-by-step instructions on safely disassembling a voltage stabilizer unit. Let's dive in and uncover the inner workings of this essential electrical component.
Objectives. At the end of this session, you will be able to dismantle a voltage stabilizer, identify sections of a voltage stabilizer, and locate the major components of various sections of a voltage stabilizer. First, let's see what a voltage stabilizer is. A voltage stabilizer is a device that regulates the flow of electricity to ensure a consistent voltage output. It is essentially a protector for electronic equipment against harmful fluctuations in the power supply. Parts of a voltage stabilizer. The main parts of a voltage stabilizer are transformer, circuit board, relay, transistors, integrated chips, preset, and input and output terminals. Now let's see each part in detail. Transformer. The transformer is the heart of a voltage stabilizer. It has both primary and secondary windings. It steps up or steps down the incoming voltage to match the desired output level. Transistors. Transistors in voltage stabilizers serve critical functions such as voltage regulation and switching, enabling precise control over output voltage levels and efficient management of power flow. Circuit board. The circuit board is the brain of the voltage stabilizer. It houses various electronic components that control the operation of the stabilizer. It includes the following parts: control unit, signal processing unit, and driver circuit. Relay. Relays are electromagnetic switches that control the flow of current in the transformer. They act like automatic switches activated by the signals from the driver circuit on the circuit board. Integrated chips. Integrated circuits, or ICs, commonly called chips, are used in voltage stabilizers to regulate and stabilize voltage levels. These chips are typically part of the control circuitry within the stabilizer. Voltage regulator. A voltage stabilizer may contain dedicated voltage regulator components such as integrated circuits, ICs, or discrete voltage regulators to ensure precise regulation of the output voltage. Input and output terminals. These terminals provide connection points for the input and output power supply lines as well as for connecting the stabilizer to the load or equipment it is protecting. Let's now see the tools and equipment required to dismantle a voltage stabilizer. We will need the following tools and equipment: trainee toolkit 1 set, DMM with probes 1 number, 500 VA voltage stabilizer automatic type with instruction manual 1 number. Let's now move to the procedure of dismantling the stabilizer for finding its major components. We can start by assembling all the necessary tools and equipment. Place them gently and neatly on the workbench. Safety tip: don't place the stabilizer on a rough surface to avoid scratches. Check that the stabilizer is not connected to the electricity power source. Now observe the stabilizer for its specifications, indications, input and output options. Now let's move to the procedure of dismantling of the stabilizer. For that, first identify and locate the screws to remove the top cover. There will be 2 types of screws, either star screw or flathead screw. Now by using the right screwdriver, unscrew in an anti-clockwise direction. First, loosen 2 threads, then remove the screws. Now gently separate the top cover. Safety tip: sometimes there may be some locks, so don't remove forcibly. Let's now locate all the important components of the voltage stabilizer. First, we will locate the transformer within the stabilizer. It is a prominent, bulky component usually positioned at the center or towards one end of the stabilizer. Look for a large, rectangular or cylindrical structure with multiple wire windings. As you can see, the transformer has 2 windings, primary and secondary. Next, we will locate the PCB circuit board. It is often situated near the transformer and may be secured to the chassis with screws or clips. The PCB houses various electronic components such as relays, transistors, diodes and fuses. Locate any relays present in the stabilizer. Relays and switches are typically located near the transformer and circuit board, where they can easily control the flow of electricity and manage various operational states. These are typically small rectangular boxes with wires connected to them. Look for voltage regulator components. These may include integrated circuits, ICs, or discrete components such as transistors or voltage regulators. Next, we will locate the diodes. Diodes can often be found near the input and output sections of the stabilizer circuit. Look for small, typically cylindrical components with a stripe indicating the cathode side. Let's now locate the Zener diode. Zener diodes are typically positioned near the voltage regulation section, close to the input or output sections. Look for small cylindrical components with a stripe indicating the cathode side, often marked with a ZD or Z, followed by a numerical value representing the breakdown voltage. Next, we will locate the capacitors. Capacitors are typically found near the input and output sections. They appear as small cylindrical or rectangular components with markings indicating capacitance and voltage ratings. Resistors. Resistors are used to limit the current flowing through certain components of the stabilizer. Resistors are integral components of feedback networks in voltage control circuits. They determine the gain and stability of operational amplifiers or other control circuits. Integrated chips. Integrated circuits, or ICs, commonly called chips, are used in voltage stabilizers to regulate and stabilize voltage levels. These chips are typically part of the control circuitry within the stabilizer. Next, we will locate the indicators. Indicators in a voltage stabilizer are typically located on the front panel or control section. They provide visual feedback on the stabilizer's status, such as power, input or output voltage levels, and overload conditions. Next, we will locate the output socket terminal. This is where electronic appliances are connected to receive stabilized power. It is usually a set of multiple sockets or a single outlet. Finally, observe the exterior and interior of the stabilizer for indicator lights, knobs, or switches. These components provide users with information about the stabilizer's status and may be located on the front panel or integrated into the PCB. After locating all the components, carefully replace the top cover of the stabilizer and secure it in place using screws. Ensure that all components are properly aligned and no wires or cables are pinched before tightening the screws.
This brings us to the end of the session. In this session, we have learned to dismantle a voltage stabilizer, identify sections of a voltage stabilizer, and locate the major components of various sections of a voltage stabilizer. Thank you for watching. We will see you in the next session. Hello and welcome to this session. In the realm of digital electronics, constructing an exclusive OR XOR gate serves as a fundamental building block for various logical operations. Leveraging the capabilities of integrated circuits, specifically the IC7404, IC7408, and IC7432, enables the creation of a robust XOR gate circuit. Moreover, incorporating concepts from analog electronics such as the series and shunt clippers can further enhance the performance and reliability of the digital circuit.
Objectives. At the end of this session, you will be able to construct the exclusive OR gate using IC 7404, 7408 and 7432. Construct the XOR gate using the simulation software. Construct clipper using the simulation software. Introduction to the exclusive OR gate. An exclusive OR gate has two inputs and one output. The output of the XOR gate will be high when any one of the inputs is high. The output of XOR gate will be low when both inputs are same. Connect the inputs A and B to the input of NOT gate 1 and 2, and also connect it to one of the inputs of AND gate 1 and 2. The output of NOT gates is connected to the input of AND gates. The output of the AND gates is connected to the inputs of the OR gate. The output of the OR gate serves as the XOR gate. Next, we will look at the construction of the XOR gate using IC 7404, 7408 and 7432 in simulation software. For this, you will need the following tools and equipment such as personal computer and simulation software installed in the personal computer. Now let's construct the XOR gate using the simulation software. Open the simulation software that is pre-installed in the PC. Click on File to create a new schematic. Now click on the new schematic. Note: Ctrl+N can be used as a shortcut for creating the new schematic. Let's place the required components for the construction of the XOR gate. For that, we need NOT gate, AND gate, OR gate and voltage sources. For placing the component on the schematic, select the component on the menu bar. Tip: For placing component, you can type P on your keyboard. In the search box, type the voltage and click on Place the component on the schematic. For this circuit, two voltage sources are required. Repeat the above step. Refer to the circuit diagram for placing the gates. Now type INV for placing the NOT gate. Repeat the above step for placing another NOT gate. Now type AND for placing the AND gate. Repeat the above step for placing another AND gate. Now type OR for placing the OR gate. Place them properly on the schematic according to the circuit diagram. Now place the ground. For placing the ground, go to the menu and select ground. After placing all the required gates on the schematic, begin the wiring between the components. For wiring, go to menu and select the option wire. Tip: For wiring shortcut, click W to start wiring. Wire according to the circuit diagram. Let's now label each logic gate. Next, we need to fix the voltage specifications. For that, first right-click on the voltage and click on Advanced. Select the pulse mode for generating the pulses between 0 and 1. Fill the values of voltage and time after selecting the pulse. The supply voltage will be 5 volts. The rise time and the fall time will be 5 nanoseconds. Time period should be twice of the time on. click OK. Next, we need to set the specification for the second voltage source. For that, repeat the same procedure. Right-click on the second voltage source and click on Advanced. Fill the values of voltage and time after selecting the pulse. The supply voltage will be 5 volts. The rise time and fall time will be 5 nanoseconds. Time period should be twice of the time on. Click OK. For labeling, select the Label Net in the menu. Select the port type. Currently we are labeling the output, so select the port as Output port. Place it at the appropriate position. Before testing the circuit, make sure that all the connections are correct. Now let's look at the clippers in detail. Clipper is a circuit that modifies the shape of a waveform by limiting or clipping its amplitude. The clipping process involves removing or flattening the portions of the waveform. Let's now see the types of clippers. They involve series clippers, shunt clippers, and biased clippers. Let's now see each in detail. Series clippers. Series clippers utilize diodes connected in series with the input signal. There are two types of series clippers. Positive series clipper. In this configuration, a diode is connected in series with the input signal in the forward direction. It removes the positive excursions of the waveform. Negative series clipper. Similar to the positive series clipper, the diode is connected in the reverse direction. It removes the negative excursions of the waveform. Shunt clippers. Shunt clippers use diodes connected in parallel with the input signal. Like series clippers, shunt clippers also have two main types. Positive shunt clipper. In this configuration, a diode is connected in parallel with the input signal, oriented such that it conducts when the signal exceeds a certain threshold voltage, clipping off the positive excursions. Negative shunt clipper. Similar to the positive shunt clipper, the diode is oriented to clip off negative excursions below a certain threshold voltage. Biased clippers. Biased clippers incorporate a bias voltage along with the input signal. The bias voltage shifts the entire waveform up or down, adjusting the threshold voltage at which clipping occurs. Biased clippers can be implemented with either series or shunt configurations. Now let's look at the procedure of constructing a series clipper. First, open the LT Spice window. To create a new file, click on New Schematic. Then select the components to construct the circuit. For that, click on the components icon. Search the components one by one from the dialog box that appears. First, search the diode and place it in the schematic. Click on Place option to place that in the schematic. Next, search for the resistor in the Components menu or simply by pressing the keyboard shortcut R and place it on the schematic. Next, search for the voltage and then place that also in the schematic. Now place the ground. For placing the ground, go to the menu and select Ground. Now we can interconnect each component by using wires. For that, click on W in the keyboard. Now we can select the specification of the diode. For that, right-click on the selected diode and click on the new diode and choose 1N4148 and click OK. Next, we need to fix the voltage specifications. For that, first right-click on the voltage and click on Advanced. Next, tick the Sign dialog box and type the DC offset, amplitude and frequency as given. And click OK. Now set the resistance value. For that, right-click on the resistor and type 1K ohms. And click OK. Finally, the entire circuit for series negative clipper is completed. Before testing the circuit, make sure that all the connections are correct. Now we will give the name for the circuit. For this, navigate to the menu and select the text. Enter the text series negative clipper. Click OK. Now to make the series positive clipper, navigate to the menu and select the duplicate mode. Select the circuit. For reversing the diode, go to the menu bar and click Ctrl+R to reverse the diode. Now we will give the name for the circuit. Navigate to the menu and select the text. Enter the text series positive clipper and click OK. For constructing the positive shunt clipper, for that, copy the circuit of the clipper and click on the new schematic. Move the components to the right place. Use Ctrl+R to rotate the components and wire accordingly. Now we will give the name of the circuit. For this, navigate to the menu and select the text. Enter the text positive shunt clipper and click OK. Now to make the shunt negative clipper, we just need to reverse the diode direction. For reversing the diode, go to menu bar and click Ctrl+R to reverse the diode. Now we will give the name for the circuit. For this, navigate to the menu and select the text. Enter the text negative shunt clipper. Click OK.
This brings us to the end of this session. In this session, we have learned construction of XOR gate using IC 7404, 7408 and 7432 with the simulation software, construction of series clipper circuits with simulation software, construction of shunt clipper circuits with simulation software. Thank you for watching. We will see you in the next session. Hello and welcome to this session where we delve into the world of circuit testing. We are exploring the effectiveness of constructed XOR gates, examining how they perform when put through their paces with various gates. But that's not all. We'll also be testing the series clipper circuit and the shunt clipper circuit.
Objectives. At the end of this session, you will be able to test the XOR gate constructed using IC 7404, 7408 and 7432 with the simulation software. Test the series clipper circuit constructed using simulation software. And test the shunt clipper circuit constructed using simulation software. Introduction to exclusive OR gate. Exclusive OR gate has two inputs and one output. The output of the XOR gate will be high when any one of the inputs is high. The output of XOR gate will be low when both inputs are same. Connect inputs A and B to the input of NOT gate 1 and 2 and also connect it to one of the inputs of AND gate 1 and 2. The output of NOT gates is connected to the input of AND gates. The output of the AND gates is connected to the inputs of the OR gate. The output of the OR gate serves as the XOR gate. Next, we will look at the construction of the XOR gate using IC 7404, 7408 and 7432 in simulation software. For this, you will need the following tools and equipment such as personal computer and simulation software installed in the personal computer. Now let's construct the XOR gate using the simulation software. Open the simulation software that is pre-installed in the PC. Now open the circuit that is previously made for testing. Now give the pulse to the inputs such as power supply 5 volts, rise time and fall time as 5 nanoseconds. This voltage source fluctuates between plus 5 volt and 0 volt in the given terminal. Time period should be twice of the time on and click OK. Before running the program, configure the analysis of the circuit. Transient analysis is used for digital circuits to understand how the circuit behaves over time, particularly during the transition between logic states. Logic states such as logic 0 and logic 1 always have the stop time twice of the maximum time period. Click OK to proceed. Label the inputs for better reference. Label as input A and input B. Now let's run the circuit. Go to the menu bar and find the Run button or else use keyboard shortcut Alt plus R. Adjust the tabs of the schematic and the output window using the tile windows. Now test the voltage source at input A using the probe. Place the cursor on the line to get probe. Input A is being plotted. Add the plotted plane below the current plot to see the plot of the next input. Move the cursor to the input B to plot the input graph. Add the plotted plane below the current plot to see the plot of output. Now we will move the cursor to the output terminal to see the XOR gate result. The output of the OR gate is plotted. Verify the graph using the truth table. Verify with truth table for all the 4 combinations. When any one of the input is high, then the output will be high. When both inputs are high or low, the output will be low. Working of clippers. Series positive clipper. Circuit configuration. In a series positive clipper, a diode is connected in series with the input signal source and a load resistor. The diode's cathode is connected to the input signal source. Operation. When the input voltage exceeds the forward bias voltage, the diode conducts, effectively shorting the signal to the forward bias voltage. Output waveform. The output waveform will have its positive peaks clipped. The clipped portion of the waveform will appear flat at this voltage level. Series negative clipper. Circuit configuration. In a series negative clipper, a diode is connected in series with the input signal source and a load resistor, but with the diode oriented in the opposite direction compared to the positive clipper. Operation. When the input voltage exceeds the reverse bias breakdown voltage of the diode conducts in reverse bias. Output waveform. The output waveform will have its negative peaks clipped. The clipped portion of the waveform will appear flat at this voltage level. Shunt positive clipper. Circuit configuration. In a shunt positive clipper, a diode is connected in parallel with the load resistor.
Namaskar, a warm welcome to all inquisitive audience. Today we are going to have a brief overview on different type of domestic paints available in the market. So first let's start with the introduction of paint. Paint can be defined as a fluid material which, when spread over a surface in the form of a thin layer, will form a solid, adherent and cohesive opaque film. Painting is normally carried out for the following reasons.